Okay, let's continue with the field measurement of evaporation. In fields, commonly in meteorology stations, we use a pan like this, which is called evaporation pan, to measure evaporation. As I told, this is evaporation is a factor of the solar radiation, wind, temperature, and other things. Here you see that we have a class A pan, which is a standard pan used entire world to measure real value of evaporation from this pan. Here we have an instrument to measure wind. You see here also with this instrument, it is called anemometer to measure the wind speed. And more details about the work, how this pan works, I can provide in this slide. Actually, up to 5 centimeter below the crest or edge of the pan, we put water in it, and after 24 hours, we can measure how much how millimeter the water surface dropped within the pan. The measurement is done through high resolution and very precise instrument that we locate in this Stirling well, and we can the instrument has for example degree of 0.2 millimeter error. Therefore, it could give us a very exact amount of evaporation. So what we measure here, it is called pan evaporation. And pan evaporation, this is a class A pan, and with this pan we assume that we model a lake here, and how much is the evaporation in this pan can be transferred to the prototype, a real lake, to calculate evaporation from lake. But before considering those pan evaporation, the value of pan evaporation, we should modify the measurements of pan evaporation using a factor which is called Kp, or pan coefficient. Pan coefficient, if you modified it, it can be considered as reference evapotranspiration. As you see, ET0. Okay, here is a question, and here the question, the slide says that commonly we can take Kp equals to 0.75 or or generally a coefficient less than 1 to reduce the amount of evaporation that we measured in pan before accepting it as a evaporation from a lake. Can you guess why we apply this correction factor? The reason behind comes back to the material that we use in construction of pan. Pan is commonly, as you see here, it is galvanized iron, and due to the temperature around it and also solar radiation, the sides of this pan will have higher degree than the size of a real lake, because it's absorbed the heat, and due to that we will have a bit more evaporation from a pan in comparison with a lake. Therefore, using pan coefficient Kp, we reduce the amount of EPAN. So we have ET0 measured from the pan from evaporation pan. And if this pan is located, for example, in such a place or such a place that has its own standard vegetation. For example, we assume that the area is mostly covered by this kind of plant. Therefore, a factor with respect to the plant, however, with respect to the standard, well watered and well organized, or we said excellent managed area, agricultural area or land, the relevant CASI should be multiplied to ET0 to find ETC, crop evapotranspiration. So you may ask, okay, where we can find those coefficients? We had so far had two coefficients, one Kp, the other Kc. For Kp, I told it's regularly can be assumed 0.75, but there are also some tables, standard values provided by FAO that you can select Kp and Kc from those standard tables. Here you see a table that shows how you can select pan coefficient, Kp. You see, for example, for case A, a pan surrounded by short green crop, okay? And because you already measure the wind, daily wind, using the anemometer that we already installed close to the pan, you can say that, okay, my wind is less than 2 meters per second, and there is upwind fetch of green crops, for example, 10 meters, and humidity was about 60%. Oh, therefore the factor is 0.75. Or based on, in the case that you have a higher speed of wind, like 8 meters per second, and the humidity is 70%, your pan evaporation coefficient can be selected as 0.65. So also Kc, for Kc we have some other tables suggested in different books, studies, or suggested by FAO. For example, for St. Augustine grass, I already showed that we commonly have in football match fields, football stadiums. The Kc could be considered 0.77. And for example, for a land like here, bell peppers, okay, this is a bell peppers growing area. Kc for calculation of ETC should be considered something between 0.8 up to 1, and even sometimes more than 1, but so close to the 1. Any question? Any question? Let's see an example to check how we use those values to solve a problem. We have a problem here, and the question says that,
teacher,
yes,
I have a problem with my internet. I sit near my friend. He also take the class. So can I do it like this?
I couldn't understand you.
Teacher, I'm Mohammed. I sit near Arda right now. We join the class together on his mobile phone because my mobile is down right now.
Okay.
Is it okay?
You can join with any place, any instrument, collaboratively with anyone. It is not. It does not matter. It does not matter for me.
Thank you.
Okay, I was solving this example. We have a class A evaporation pan and water depths in the pan in 1 day or on day one, yeah, before measurements was 150 millimeter. At the same day, we have a rainfall, 1 millimeter rainfall, okay? And the water depths in pan on day two or after 24 hours, yeah, in the pan, class A pan was 144 millimeter. So the question says as determine pan evaporation, reference evaporation, reference evapotranspiration, ET0, and crop evapotranspiration for irrigated grass pasture in Central California. So first, in order to calculate EPAN, we can say that, okay, I said that pan evaporation equals to the amount of water before the day and amount of water after the day. If you subtract those, it gives you amount of evaporation. However, we have 1 millimeter extra rainfall during that day. Therefore, we add those water to the amount of water that we had at the beginning. And from these calculations, I can find that pan evaporation equals to 7 millimeter per day, or in that day was 7 millimeter. So I have to adjust the pan evaporation using pan coefficient. And as suggested in the previous slide, it could be considered 0.75. Because in this question, you see, I don't have the wind information about wind. Therefore, I can't go to the table to select another coefficient. Therefore, the suggested coefficient is 0.75. Now I have ET0 and I can answer two parts. And for the last part, I need to find Kc to modify this value, okay? Kc should be selected from a table that represents irrigated grass pasture in Central California. So the relevant value equals to 0.76 that you can use this table. You see here I have irrigated grass pasture in Central California and Kc is 0.76. Therefore, I multiplied the ET0 5.3 in Kc 0.76. Therefore, the crop evapotranspiration for that day should be 4 millimeter. So we can consider that 4 millimeter of water in that day from those land covered by grass pasture or from those irrigated grass pasture will be lost. We will have loss 4 millimeter loss of water due to evapotranspiration in that area. The second example discuss how we calculate the annual evapotranspiration. And to do this, we have to find monthly evaporation or total amount of evapotranspiration in 1 month, and then you add all together. That gives you annual amount of evapotranspiration. For example, here you see that in a given area, we had such cultivation activities in different months. For example, in January, they had rice, they harvesting rice. In February, groundnut. In March, development. It was the development season of the groundnut. This is groundnut. You see here. You see that at different times there is different pattern of cultivation on the ground. And from June to the end of the year, they had sugar cane. Okay, so these are KCs, factors of the standard factors for those crops. And here you see the monthly pan evaporation. What is the monthly pan evaporation? Is some of the daily evaporation, okay? Some of the daily evaporation, which finally is averaged on a month. For example, at day one, we have, at January, day one, we have 2 millimeter, day two, 3 millimeter, day four, 4 millimeter, day five, 1.5 millimeter. If you add all together and get the average of a month, it gives you mean monthly pan evaporation. So if you multiply this value to the KC, you can find the ETC for January. The same process is done for the other months, and you can create such a table, okay? For January, the measurement from field measurement, we found average monthly. These are KC. And if you multiply these together, it gives you mean monthly crop evaporation, ETC. Here we showed EC, but it is ETC, crop evaporation or crop evapotranspiration. And if you multiply this value to the number of days of that month, it gives you total evapotranspiration for a month in millimeter. And you know, for example, here we multiply 1.69 to the 30 or 31 if it is January. And for the same process is done for the other months, and some of those total monthly amount of ETC gives you annual evapotranspiration from that area. Okay, there are also some other instruments that we can use to calculate the evapotranspiration directly. So far, we used pan evaporation, then adjusted it with respect to the crop type and crop season. But is it applicable or is it possible to measure transpiration directly? The answer is yes. For this aim, we use lysimeter. You see lysimeter are devices, typically tanks like these, tanks or containers that define a specific boundary to contain soil water and permit measurement of either the soil-water balance or the volume of water percolates vertically and or its quality. Lysimeters can be broadly defined as percolation lysimeter, like some here you see, sometimes also called drainage lysimeters, or weighting lysimeters. Both can serve the purpose of determining the soil-water balance and the vertical percolation flux, drainage, and the chemistry of the percolating water. Actually, how it works, maybe this slide shows you more information. You know, as I told, this is a sample of the same area, okay, a sample of the same area, and we isolated those sample using this tank, okay, isolated the sample. What I mean by isolating, this iron wall of the container does not allow any water moves outside or comes from outside into the container. And then after isolating the sample, we put it into the ground like this. This is the top view of this container, top view. that shows the same sample, for example, and this is bottom view, what we have underground, okay? From here, maybe there is stairs to go underground. And this is our container underground. There is a tube, like here, you see a hose that allows you to measure the percolation or amount of water that that goes out from the tank. At the beginning, and these instruments, you hear these instruments also allows to measure the weight of the isolated area of soil and crop at the beginning and, for example, after a day, okay? And after a day, when you measure the difference between the weights, and when you know how much water goes up, therefore you can use water balance equation that we already talked about water balance equation to find the loss. And here loss is nothing than evapotranspiration, because we have some soil, we have vegetation, and therefore we directly measured, not directly measured, we measured some values that we can use water balance equation to see, to check what is the amount of evapotranspiration. Okay, lysimeter is a device in which a volume of soil planted with vegetation is located in a container to isolate it hydrologically from the surrounding soil, having a weighting device and a drainage system which permit continuous measurements of excess water and drainage below the root zone and plant water use, and hence evapotranspiration. The amount of water lost by evapotranspiration can be worked out by calculating the difference between the weight before and after the precipitation input. If you have precipitation input, or if you have some given amount of irrigation water. Okay, so this is the equation that originated from a water balance. You remember, input minus outputs equals to delta S over the time. And here, if your delta T or time is 1 day, you can calculate ET. These are your inputs and outputs explained here. Our output is, one of the output is evapotranspiration. We are looking for it. And precipitation is input. Irrigation water is input, but excess water drained from bottom, it is output from the system. The container is our control volume, and delta S is given here. Actually, S is increase or decrease in storage of soil moisture. Therefore, S can be appeared here as a positive or negative, with positive or negative coefficient if it is increase or decrease in the storage of water. So this is it was a practical method to calculate evapotranspiration. However, we have also some other formulations to calculate. These are mostly empirical formulas that we use to calculate evapotranspiration. For example, to calculate PET, or potential evapotranspiration, you remember the definition? This is the full amount of evapotranspiration from a region when there is no water limitation. Thorne's weight method. Thorne's weight method is this. We can use it for calculation of PET at a month. The I is monthly Thorne's weight heat index, which is equals to T over 5 to the power of something, and T is the means monthly temperature. And then we use, for example, first we calculate I, then we modify I for monthly for the annual by summation of all I's at each month. You see that I is a function of temperature, is a function of mean temperature. And then we use this formula to calculate PET. For a region, here we have alpha, which described here, and I, which already given here, and also T is the time, which is 30 days for a month. Then this value is also adjusted based on the number of, for the annual PET, based on the number of days in a month and number of the months that you calculated divided by 12 months in a year. So trans weight is one way to calculate PET, the trans weight equation. We have also Hargreaves equation. In Hargreaves equation, we use maximum, minimum, and average temperature of a day, and also radiation, extraterrestrial radiation. Extraterrestrial radiation is the radiation that we have outside the Earth's atmosphere, and this formula can be used to calculate evapotranspiration. We have also net radiation methods. Here we use this formula based on net radiation and average temperature. We can get an estimation about evapotranspiration in a region. Yeah, so therefore you know three other equations: trans weight equation, Hargreaves equation, and net radiation based method. I summarized again those factors affecting evapotranspiration. Already talked energy availability, humidity gradient, water availability, wind speed. Physical attributes of vegetation and soil characteristics are of the most important factors that affects the amount of evapotranspiration in a region. From the physical attributes of vegetation, from this perspective, I also would like to define leaf area index, LAI, which is the sum of the leaf area over the soil area on a region. You see, based on different types of leaves, it is possible that leaf area is higher than soil area, and this index shows that if the amount of transpiration is higher than amount of land evaporation, or vice versa. And yeah, that's all for today, and that's all for